the 2D conceptual development of torque, up to and including equations through the concepts of rotational and translational equilibrium. To say that an object is in translational equilibrium is to say that the object has a constant velocity in each dimension of travel. More clearly, the object is said to have translational equilibrium when it is not accelerating. To ensure that a sub x y equals 0 meters per second squared, we must ensure F net in the x dimension is equal to 0 newtons, and F net in the y dimension is equal to 0 newtons. We say that an object is in rotational equilibrium when the forces acting with a tendency to cause the object to rotate about a fixed axis are in balance. Rotational equilibrium for an object will require not only translational equilibrium, but also that the rotational effects of the forces be balanced so as to prevent rotation. The effect of an applied force on an object's rotational tendency is dependent on two things: the percentage of the force acting to accelerate the body about the axis of rotation, that is, the percentage of the force not acting through the axis of rotation, and two, the distance from the axis of rotation to the location of the applied force. The percentage of a force not acting through the axis of rotation can be determined by multiplying the magnitude of the applied force by the sine of the angle made between a line contained in the plane in which the force acts, extended from the axis of rotation to the force. I've included two drawings. One is a two-dimensional drawing. You're looking straight at a disc and a force applied to that disc. That force is applied at 90 degrees to the disc, meaning on a tangent. And we can see that the distance measured to the point of application of that applied force is measured from the axis of rotation. Second example is a 3D version of the same. It is important to know that the axis of rotation is not necessarily where the object is, though in our problem set it will be for mathematical simplicity. The solid disk attached to the axis of symmetry can be cut into any shape, remaining attached to the axis, and still provide the identical conditions for applying the force F. Note, a force, being a vector, cannot cause an object to have a tendency to rotate opposite directions about an axis simultaneously. The force will have a tendency to motivate either a clockwise or a counterclockwise rotation about the axis. The product of the defined distance and applied force acting perpendicular to that measured distance is called torque. Though we have established our concepts of torque using a flat 2D disk, the concepts can easily be extended into 3D by replacing the disk with a solid cylinder. Torque. When a force does not act through the center of an object's mass, it can, dependent on chosen direction, create torque about any axis drawn through that center of mass. Torque motivates rotation about the center of mass. The tendency to motivate the rotation is dependent on two things, as we have seen. One, the magnitude of the force, and two, the radius of the disk to which the force could be applied at a tangent in order to motivate the same rotation about the axis. The mass impedes the rate at which the object can be accelerated in its spin. We will not consider acceleration in our equilibrium unit involving torque. Since the torque increases with the magnitude of the force, and the torque increases as the radius of the imaginary disk increases, we define the magnitude of torque by the formula tau equals F sine phi times d, where phi is the angle made between the applied force F and the displacement between the axis of rotation and the point of force application. For rotational equilibrium, the sum of the torques with a tendency to create counterclockwise rotation must equal the sum of the torques whose tendency is to create clockwise rotation. Rotational equilibrium also requires the conditions for translational equilibrium. You can now view Physics 12 equilibrium sample problems.